Hello and welcome back. In today's video, we are going to start another video which is a transient heat conduction with heat generation, another problem that we will be studying here. So this will probably be the last video from the pure conduction tutorial side, and next we are going to start with the pure convection heat transfer problems. Now today's problem, we have a numerical problem in which we have a thin wall of thickness 0.01 meter, and it is generating heat at a constant rate of q dot watt per meter cube. It's initially at 300 Kelvin, and the surfaces are also at 300 Kelvin. This is because keeping the we are keeping the surface temperature effect of temperature of the surfaces on the temperature distribution. We are keeping it negligible, or we are not introducing the effect of these surface temperatures. We are only going to focus on the heat being generated by the domain and what will be the temperature distribution due to that heat generation. That's why we're going to keep the initial and the surface temperature the same. So our thermal physical properties are given, q dot is given, and the initial and T surface are same. We are going to find the temperature at the center. So this is the total thickness. Center will be 0.005 meters, and time after 60 seconds we are going to find the temperature. Now this is our final solution equation in the form of infinite series, and as usual, as we saw in the previous videos, the solution is going to lie in the first term. We are going to use the first term approximation, and for higher terms will contribute the contribution of the higher terms will be negligible. So for this we need Fourier number, and for Fourier number we need alpha, thermal diffusivity. So we are going to start with the thermal diffusivity. So thermal diffusivity is K by rho Cp. All these K rho Cp values are given, and we will calculate the alpha value first. Since it's a COMSOL tutorial, so that's why I am moving fast here as I keep on saying these things. So next point is Fourier number. So Fourier number is alpha T divided by L square. L is thickness, T is our time at which we want, after which we want to calculate this Fourier number, and alpha we found above, so we will find the Fourier number. Now Fourier number is here greater than 0.3. That's why this solution is applicable. We can use this series solution. If it is much lesser than 0.3, then we have other alternative forms of the solution that we can use. For much greater than 0.3, this series solution exists. This is all from the theory. That's why I'm moving quickly. Now location of interest for us, as I said, 0.05 meter. X is equal to 0.05 meter. Now we'll calculate all these terms for our this solution. So we'll start with Q dot L by K square. If we see previous, see this is the TS term. This is the surface temperature, which is 300 Kelvin. So our solution is, our final solution will be at 0.005 meter location. After 60 seconds it will be 300 plus something. This is 300 we know, and we have to deal with this something first. So for this something, we have first term Q dot L square by K. So Q dot L square by K, we will calculate. Q dot is given, L is the thickness, K is given, it is 5. Then we calculate. Now the next term is this 1 divided by 2 something. So it is this 1 divided by 2, 1 minus x. Since we are calculating at the center, so x is 0.005 and L is the thickness 0.01. So when we do 1 by 2, 1 minus 0.005 square divided by 0.01 square, we get this term. 0.375. Then next we have this summation term. This is where series goes to infinity. So where we will use n is equal to 1 only. We have these terms here term number 1, term 2, term 3. We have three terms: cos term, exponential term, and 4 by pi cube. So this reduces to 4 by pi cube for n is equal to 1. So this is one term. Another term is for this cos, which reduces to n divided by 2. This is pi 0.005 divided by 2 into 0.01. So next term reduces to this pi by 2. So this next term reduces to this cos of pi by 2, or this is this cos of pi by 2 into 0.005 divided by 0.01. So we know this is pi by 2, and we know this is its half clearly. So this is again 1 by 2 because the center point of this. So 1 by 2. So this is basically cos of pi divided by 4. This is this term. So we have 4 by pi cube term. We have this term. Then we have this exponential term here. This exponent of this 2 1 is 2, and 2 minus 1 is 1. 1 square is again 1. So we have pi square Fourier number by 4. So we have pi square Fourier number divided by 4. We have these three terms. So first term is when we calculate cos of pi by 4 is 0.707, exponent of pi squared FOV Fourier number we found divided by 4, it will be this. Then 4 divided by pi cube, it will be this. Then so for our first term will contain three terms basically. So term 1 is 0.07 into 0.129 and into 4.9 10 to the power minus 4 this. So our first term will be the product of these three. So our first term becomes 4.5 times 10 to the power minus 5. These are this term. So we calculate all the terms. So our solution is basically here tx of t. So this is basically t x comma t, which is 300, this 300 plus 5 times 0.035 1 by 2 term 375 0.375 minus 0.000045, which is this 4.5 times 10 to the power minus 5. So combining all these terms, we get temperature at the center location after 60 seconds approximately 300 0.87, which approximately 301 Kelvin. We can keep it in mind that it is 301 Kelvin. Now we'll solve the same problem using COMSOL Multiphysics, and we will check the two numerical solutions. And we will go to geometry, and we will create our rectangular. Since the wall is basically 3D, but we are interested in only one dimensional heat transfer, so we'll take only the one side of the wall, which will be the rectangular, and we know that its width is 0.01 and its height can be anything. We're interested in the width, so let's keep height 0.1. This is the wall, so this is the front side of the wall. So we also need a point at which we have to calculate this temperature. We will go to primitives, then point. The point has to be at the center. So since our point has to be at the center, so it will be center point will be x is equal to 0.005 and y will be 0.1 is half, which is 0.05. We'll build it. Yeah, we have a point at the center. This is required for the evaluation of the temperature. So we will go to solid. We will input our k value, and this k value is, if we check from the problem, this k value is 20, rho is 7800, and cp is 500, and q dot is 10 to the power 6 here. So we'll go to COMSOL back. So our k value is 50 in SI units. Our rho value is 7800. and Cp is 500. Cp is 500. Then initial values, then initially it is at 300, and we'll apply temperature at this side, which is again 300. We're keeping it same to see the effect of the heat generation on the temperature distribution or temperature at the center point. So we need to include the heat generation, which is in the heat source. We're selecting heat source, and it is heat sources by default is selected in watt per meter cube. This is what we have given, 10 to the power 6. So this 10 to the power 6 watt per meter cube, and we have to select the domain. Now this is generating this amount of heat. Now we go to mesh, we build all, we'll make it finer, we make extra fine to get the solution accurately. We'll go to time dependent study, and we'll start with time with 0, and we'll use time step of say 5 seconds, and we'll calculate it up to 60 seconds because we need a temperature at the center after 60 seconds. We'll hit compute. When we hit compute, we go to derived values because this is where our obtained data is. We'll choose point evaluation for our point, and we'll choose that point that we made earlier, and we will hit evaluate, and we'll see after 60 seconds the temperature is 300.25 at the center. And if we compare it with our analytical solution, which is also 301, so the temperatures are close. Since the wall is very thin, so there is time is only 60 seconds, the temperature change will not be that much. So we are getting here 301 Kelvin, and in COMSOL we are also getting around 300.25 Kelvin temperature. So this confirms the analytical solution, and the confirmation is from COMSOL Multiphysics. That will be all in today's video. Thank you.